So, hello everyone. As I said, good morning and good afternoon for you. And I'm really good today. It's good to know that I'm recovering from my flu. And the last week, as I said, I was in a field work, and unhappily, I didn't have time enough to record our class. Only on Saturday, I have uh, really time to spend some time in my computer, but I realized that, okay, if I record a class now on Saturday, people they will not have a lot of time to watch the video before our class today on Monday. So I decide that yes, let's do our class today on Monday, and tomorrow I will share a new record about the class last week. Okay, so you have time to watch our class today, and you have time enough to watch the next record that I will share tomorrow. Okay, so yes, let's start our class. Um, okay, we already talked about this, about the basic definitions. I think that someone raised the hand. No, no. Okay, great. It's just comments. Great, great. No problem. Let's find where we stop at. We already talked about each type of horizon and also about the soil formation factors. So everyone knows now very good definitions about the soils and how soils are formed and everything else. And we can start to get deeper in the soil taxonomy. And yes, this is one of the points that need to start now. Now that everyone knows very well about horizons and layers, and everyone knows very well about the properties and characteristics of each of these horizons and layers, we need to talk about the suffixes. These suffixes, they are letters that we add in the master horizons, especially the master horizons, and in some cases also in the layers to express one specific characteristic, one specific property. For example, if that specific horizon or layer that I'm describing in the field, it has some shiny surfaces, some faces that shine when I expose the soil to the sunlight. Or, for example, I also can see some crystals like salt crystals or carbonate crystals. So these properties that I can describe and identify in the field, they are related to some suffixes. Those suffixes, they express one specific information that tells you, okay, this horizon or this layer, it has some specific properties. And these properties, they are quite important when I will start the soil classification process. Okay, so the first step after describe and identify in the field which layers and horizons I can see standing in front of the soil. Now I will start to think about the suffixes, okay? Which properties and characteristics each of these horizons and layers they possess, okay? And of course, guys, we have a lot of suffixes. We have a lot of them. So you don't need to memorize them, all of them, okay? Because we have books for this. You can just check on the soil taxonomy book, on the field book description, on the Word Reference Base for Soil Resources book, the WRB book, and you can find these suffixes. Of course, after some time, you start to memorize some of them according to your experience. For example, oh, I work more with soils with carbonates. So easily I will record the latter, the suffixes related to these carbonates. But it's quite hard to memorize everything. So don't worry about it. I will just show you all the options, and you just need to think, okay, I need to consider these kind of properties when I start to describe the soil before actually classify the soil. I need to add suffixes in each horizon or each layer. Of course, some horizons and some layers, they do not present a suffix. No problem with that, okay? But the majority of them, they really have at least one. Sometimes we have more than one suffix. I will show you some of these examples in the future, but we can have, for example, a horizon with 2, 3, or even 4 suffixes because it has glade properties, so glade colors, gray colors. I also can see some nodules, like iron nodules, but I also can see some crystallization of salts, and I can see some shiny faces. So we have a lot of different properties, and for each of these properties, I register a suffix, a specific letter. Okay, so don't worry trying to memorize everything because you can check them on the books, but think that, okay, they means something. They brings some information during the soil classification process, during the soil classification and description, okay? So let's start with the basic, one of the most easiest and simple. It's a suffixes related to the O horizon. And oh, JJ, I cannot remember very well what is the O horizon or the O layer. The O horizon or the O layer, they are related to a high content of organic carbon, okay? So when I see something like this, like in this photo, I can see a very dark material. And if we were in the field, we also could feel that this specific section, it has a very light density. So I can easily take a large piece of soil without any kind of material, just using my hands, because the density of this material is quite light. So I can easily try to extract some of these materials, and I can see this very dark color of materials that are partially decomposed, and then they produce what we call melanization. They are darkening these horizons, okay? We add 3 possible suffixes according to the stage of the composition of this material, okay? If the organic matter is highly decomposed, so I can see a very low content of rubber fiber or materials that are just easily or partially or non-decomposed, but the content of this material is quite low, so I will add the letter A. Okay, so I can see that this specific layer or horizon has a huge amount of highly decomposed material, and the low decomposed organic matter express a content less than 17% by volume. So in this case, I need to add the letter A. In the opposite, if I register a huge amount of material that it's slightly or low decomposed, so I will add the letter I. So if the content of low decomposed organic matter is equal or higher than 40%, so I will add the letter I. Okay, so I see that the content of material, it's basically low decomposed organic matter. I can easily see the leaves, the roots, the timber, everything. It's quite easy to see the nature of the organic matter because it's very low decomposed. So I will use the letter I. And the E is in the middle. If I register an intermediate stage of decomposed material. So I can see that the content of materials that are low decomposed varies between 17 and 40%. So I will use the letter E, okay? We have much more precise ways to measure this, but especially on the lab. At the field, we just try to check this. How can we do that very easily, JJ? When you took a piece of soil, when you took a piece of these layers, these organic layers, you just can mix them with water and do this kind of movement, like some with some friction. This kind of friction will release all the highly decomposed organic material, and you will keep only those materials, the fibers and everything that's low decomposed. So you can see the change of volume between the material that you took in the beginning and after the friction. And between, according to this variation, you can measure, you can have an idea actually how much of highly and slightly decomposed organic matter you have in that specific horizon or layer. Okay, and then you can add one of these three suffixes. Of course, you don't need to do this if you are talking about a horizon or a layer that has a low organic carbon content, or at least lower than 12%. Okay, so if, for example, I cannot see very dark colors, I cannot see a low density, so the material is quite heavy, the color is not too dark, so that horizon or layer has a low organic carbon content. So okay, I don't need to check this by friction, the content of organic matter, and check or try to measure how highly or slightly decomposed is that material. Okay, I only will do that for horizons and layers that has a high organic matter content, that has a high organic carbon content, that has low density and very dark colors. Okay. One of the suffixes that we can use to O and A horizons are the P and U. And in the both cases, we are talking about human disturbance, human action, okay? In the case of the P, we use the P letter, the P suffix, to express human action in the surface, okay, in the O or A horizons that express some kind of, let's say, modern action, like humans are adding some nutrients by fertilizers, or they are mixing the soil for agriculture, they are plowing or doing some pasture, they are compacting any kind of this material related to agriculture and ancient activities. We use the letter P. And the letter U, it's more related to artifacts. So if I can see some kind of asphalt, bricks, plastic, glass, metals, or anything in the surface, at the surface, I use the letter U. Okay, so both letters, they are related to human actions, but one of them is more related to ancient action and or agriculture and pasture, and the other are more related to modern action or artifacts, something that humans can add in the soil. Okay. We also have some suffixes that can be applied to all horizons and all layers, okay? For example, is the case of presence of calcium sulfate, the gypsum or any anhydrite presence in the soil should be described. So I can register gypsum or anhydrite calcium sulfate in any of the horizons. We usually see it in the surface, at the surface, but I can see these horizons in, I can see these minerals in all soil profile, in all depth of the soil profile. So when I see it, I just need to report, okay? So if I can see the anhydrite, only this calcium sulfate without water, I use the letter AA. If I can see the gypsum, that's calcium sulfate plus water with less than 50% of volume, I use the letter Y. And if I register a huge amount of gypsum, more than 50% of volume, and light colors, and all of this gypsum, it's related to pedogenic formation, okay? And then I will use the double Y, okay? This this AA suffix, it's quite hard for now, because hardly we can identify in the field or distinguish in the field the difference between gypsum and anhydrite. Of course, if you are in a very, very dry condition in a desert, it's quite probable that you are talking about anhydrite, but and if you are talking about an area that has a high evapotranspiration, but also has a lot of water, so for example, you are quite close to a coast or you are close to a mangrove, so probably we are talking about gypsum, but we need to be sure. So we are trying to identify some criteria that can help us to identify anhydrite and gypsum at the field. Of course, we don't need to be 100% sure at the field, okay? We can just say, okay, I have some calcium sulfate concentration, but I'm not sure, or I'm not 100% sure if I have anhydrite or gypsum. No problem. Just mention both, and after some lab analysis, especially the XRD analysis, you can define, okay, JJ, I have anhydrite, or I have gypsum, or I have both. It's quite uncommon to have both, but yes, they can occur. And you also can identify the amount of gypsum in this specific case if you have gypsum. Okay, so some lab analysis, especially XRD, can help you very well to identify which of suffixes you should use, okay? Oh, here is just some examples showing that, especially at the surface, you can see some crystals, like this white crystals. The color looks like milk, okay? And when you just drop some acid, you cannot see any kind of bubble, showing that this is not calcium carbonate, they are salts. And then, okay, probably they are gypsum, or probably they are anhydrite. I can check in the lab using XRD. This one, it's also used to all horizons and layers except organic materials, okay? And in this case, we use the letter B to buried genetic horizons, okay? So in this case, in this photo, I think that if you pay a lot of attention, you can see here close to 30, 35, and 40 centimeters, you can see a darker color than, for example, here. So this horizon is a buried horizon. And this photo will be much more easier. In the past, I described this soil profile, and you can see very, very easily here a darker color than the surface. So this is a buried horizon. Is a buried A horizon. So in this case, I will use the letter A, the capital A, and the B as a suffix. The AB in this case means that this horizon, this dark horizon, was a horizon in the past. It was formed at the surface, but something happened, and now this A horizon that was formed at the surface is buried. So some erosion movement, some kind of material was eroded and now buried this past A or past surface horizon. So to differentiate this past surface horizon to the modern A horizon that's at the surface, I use the letter B, okay? You need to consider that this letter, it's only used to horizons and layers that were buried, okay? So some horizons, they are not buried in the beginning, but they can be buried after that. For example, a B horizon. A B horizon already, it's formed let's say, buried, because it's not formed at the surface, it's formed at subsurface. But even at subsurface, horizon can be buried. How can you do that? For example, let's say that I have an A and a B horizon. And then after some time, this A horizon, it's completed eroded. It's completed erased. So now the B horizon, it's at the surface. And after some time, this B horizon can be buried by something. And for example, I can have now A horizon, a C horizon, and a B horizon. And this B horizon was buried. So this B horizon, I should indicate with the suffix B, indicating that it was buried, okay? This is quite common in the tropic, guys. In the tropics, we can see a lot of B horizons that were buried, A and B horizons that were buried, okay? So just need to pay attention for this. This suffix, it's quite important for people that really want to study soil genesis and, of course, soil classification. And so you just need to pay attention for that, okay? We have some criteria to identify and to differentiate B horizons and A horizons that were buried than the others that never were buried. We need to talk about this later when we talk about lithic discontinuities, okay? But yes, we have some criteria and some methods that helps you to identify these buried materials. Okay, after some times, after you having some experience, it's quite easy to identify them in the field. Oh, another suffix that also can be used for everything is the Z suffix. The Z suffix express accumulation of salts that are more soluble than gypsum. You can just solve them with cold water. So you just, if you bring some cold water to the field work, you can try to dissolve them. If they dissolve, yes, we have other kind of salts, not only or no gypsum, okay? And in this case, we use the letter Z. You can see a lot of them here in this photo. They have this white and very light color. They are especially concentrated at the surface, but yes, you can see in all horizons, B, C, E horizons, they are in all depths and all horizons that you can imagine. They are more common at the surface because, of course, at the surface, we have, in general, the highest temperature. So because of this highest temperature, we have the lowest content of water, and because of this, we have a higher concentration of salts and higher precipitation of salts. This one, I love this suffix. I really love because it's quite common in the tropics and tells you a lot about the landscape evolution. Is the C. The C suffix express concentration or presence of concretions or nodules. Okay, and here we have a very good thing that we need to describe and define now. The difference between concretions and nodules, okay? The concretions, they have an internal fabric, an internal organization. So you can see some kind of structures like layers. Very good example, it's like an onion. If you cut an onion, you can see in the onion, in the middle of onion, a lot of layers, concentric layers. So in this case, you have a concretion because the concretion, they have an internal fabric, they have an internal organization, they have structures that are different from the others. The nodules, they don't have any internal fabric. They don't have an internal organization or structures. So for example, I broke this piece of material and you cannot see any kind of internal fabric or internal organization or any layer inside this material. So in this case, you are standing a nodule. You are seeing a nodule, okay? The external face, it's equal for both concretions and nodules. They are basically the same. Of course, we have some variations of colors. Some of them are redder, some of them are yellow, but okay, no problem. And also the size of these materials, they can be larger or thinner, no problem, but both are enriched in iron. Not only iron, but also aluminum, manganese, and titanium. Okay, this specific material, it's more common to be rich in iron because iron is much more common than these elements in the soil in the oxide formation. Okay, so it's quite common to see some soil cemented by iron, but you also can see some aluminum, manganese, and titanium cementation. Okay, we use this C suffix for everything, but we need to exclude any kind of cementation by silica, and we also need to exclude any kind of cementation by carbonates or salts. Okay, so we only use this, let's see, for metals. When you have metals or transitional metals or semi-metals, yes, you can include them. Okay, no carbonates and no salts and no silica. In this case, great, we can have any kind of cementation. Why I like them very, very, very much? Because they express change of redox conditions. Okay, express the iron concretions and the iron nodules. They express that in the past we have something that was flooded. So we have a flooded environment that induced reduction of iron, reduction of manganese, and some change in the landscape induced now the oxidation of these elements. So especially iron and manganese, they can easily oxidize, and when we change from iron 2 to iron 3, you can start to induce an oxidation of the material, and the formation of goethite and hematite now will act more like a gel, and this gel starts to cement soil. It's why you can easily see here some quartz crystals. These quartz crystals are crystals that were inside the soil, but they were cemented by iron, and now I have a body of soil that were cemented by iron and or manganese and or aluminum and or titanium. Okay, these bodies, they are really, really hard, so it's quite hard to break them. They are very, very strong and dense. They have a very high density. Soils that register a high content of concretions or nodules, like this one, you can see that all these pebbles and gravels, they are not rock fragments, they are concretions. Okay, in this specific case, it's quite hard for the agriculture, for pasture, for any other kind of land use, because it's quite hard to root growing in some areas. Not in this case, you can see roots even here, even close to 110 centimeters depth, but in some cases, the content of concretions and nodules is quite hard, and because of this, the roots can have some problems to grow, and of course, the agriculture will be less productive, the pasture will be less productive. Okay, depends on the area and depends on the size and the amount of these concretions and nodules to have some huge or less problematic situations in the soil. Okay, we'll talk about more then in the future, because I really like this kind of soil profiles. They, as I said, tells you a lot. They tells you that that specific area has an abrupt change of age of redox and oxic conditions, showing that in the past this area was flooded and now is not flooded anymore. So I can understand much better about the landscape evolution, about soil genesis, and about a lot of things. For agriculture, as I said, it's quite hard, but people They are really trying to increase the productivity of agriculture in this kind of soils, because we have a lot of these soils in the tropics. So it's a kind of adventure, and we are trying to improve, trying to solve the low fertility of the soils, but at the same time, some physical problems that we also have. But yes, people are starting to work on them. We also have some letters that express thermal conditions, especially for permafrost, that we know that are related to very low temperatures. Okay, we already saw that we have a specific layer related to water content, and we have the water that's frozen, that's the WF, and the F is used because of the presence of permafrost. Permafrost is just a layer that registers temperatures lower than 0 Celsius for at least 2 consecutive years. So I need to register very low temperatures, and because of these very low temperatures, the water is frozen, and then I will add the letter F. The letter F can be used to W, horizon and layer, but also can use it to other horizons and layers, okay? As soon as I can see frozen water, okay? In some cases, I also can see the dry permafrost. The dry permafrost, it's more common in the driest regions of Antarctica, in the areas that I don't have even water, even a high amount of water that can be frozen. So I can register very low temperatures like -10, -10, 13, -50 Celsius degree, but I cannot see frozen water because I don't have water in the system. It's too dry to register water, okay? So the coldest deserts, the driest deserts in Antarctica, they register dry permafrost, not the regular permafrost with the frozen water. So in this case, I use the double F. Okay, in this picture, I know it's too dark, but if you pay attention, you can see here below 55 centimeters, you can see like a blue layer. This blue layer is the permafrost. In this case, the typical permafrost. Okay, this is just frozen water because of the very low temperature in Antarctica. We also have in Antarctica, talking about Antarctica and talking about periglacial areas, we have some evidences of cryoturbation. Okay, I will talk a little more about this when we start to talk about jelly salts, but cryoturbation is one specific process of mixing of soil. Okay, the process of thawing and freezing, shrinking and swelling of the soil because the change of temperature and the change of physical state of the water between liquid and solid, this could induce some mixing. So things like the termites, we already know that the termites can mix the soil. Yes, they can do that. But also change of temperature. The change between not high, but let's say medium temperatures, like temperatures above 0 Celsius degree, like 1, 2, 10 Celsius degree in the summer, and very low temperatures, sub-zero temperatures in the winter. This change of temperature could mix the soil, could induce some mixing and migration, especially migration of clay from the deepest horizons to the surface. This migration of clay can induce some mixing of material, and then we can see some features that express what we call cryoturbation. Okay, you can see in this very, very shallow soil profile that we have darker spots here and here, especially here and here too. These darker spots They are organic matter spots, and they are producing by cryoturbation. This mixing of material can bring some organic material from the surface to the deepest horizons. And then this is one of the evidence that yes, we have some mixing of soil. We have some mixing of material that we call cryoturbation. Okay. It's quite common to see also some irregular or broken horizons, some sorted rock fragments showing that we have this kind of feature. I will show you this. Okay, at the microscope, we can see some banded fabric showing that yes, we have this changing of solid and liquid physical states of water, some shrinking and swelling of the material, some thawing and freezing of the water. This sample I took is an undisturbed sample, and if you pay attention, you can see that in the middle of the sample, I'm sorry, we have a darker, a redder color than the opposite layers, than the borders. This darker color, this reddish color, it's related to this clay plume, this clay assumption, this clay migration from the deepest horizons to the top. Okay, so this darker color shows you that you have some migration of clay from the deepest horizons to the surface. Okay, and this darker color is related to a higher clay content here than the borders. And you can see very easily that the borders has a higher content of gravels, especially large gravels. Okay, this clay migration, it's what we call cryoturbation and can induce some of the features that we already saw, and also these features. These features, they are called partner ground. They are related to some circles and other kind of geometric polygons produced by the clay migration. The clay migration from deepest horizons to the surface induce a concentration of clay in the middle of these polygons, and this movement exclude or select these gravels and keep them in the borders of the polygons. So you can see very easily that in the borders of the polygons, I have a higher content of gravels, and in the middle, it seems a lower content and a higher content of clay. These polygons, they are impressive. You can see the size of the people here and the size of these gravels. They express that in this specific area, I register cryoturbation, and the cryoturbation, it's only formed close to in areas that we have permafrost close to the surface. Okay, so even if I cannot identify the permafrost in this case, I already know that it's close to the surface because the cryoturbation is related to this change of temperature. The cryoturbation can be very easy explained when you think about the winter and summer in Antarctica or Arctic, or very areas that register a very high variation of temperature between summer and winter, but at least in the winter you register sub-zero temperatures. Okay, so for example, in the winter you start some snow starts to snowing, so you have a deep layer of snow at the surface of the soil. Great, no problem. After that, when the summer arrives and you start to register some positive temperatures, the snow starts to melt, and the melting of snow starts to yield some water that can penetrate through the soil and achieve the permafrost. The permafrost, as I said, is that layer with very low temperature. And if this permafrost is a typical permafrost, means that it is a frozen layer. This frozen layer cannot allow water to migrate, so water cannot penetrate through permafrost. So you start to concentrate water in the deepest horizon, in the contact between the permafrost and the soil that's not frozen, okay? And in that specific depth, you have positive temperatures, no problem. But when the winter comes again, so you have a very abrupt variation of temperature, because at the surface, because of the air temperature getting down and down and down, you have a very low temperature at the surface, and you register positive of at least higher temperatures at the deepest horizons of the soil. So you have a abrupt potential variation of temperature between very low temperatures at the surface and positive or higher temperatures in the deepest horizons. This difference of temperature induces water migration and clay migration. So the water that comes from the melting of snow and it is in the deepest horizon, it starts to migrate against the gravity, and the water starts to migrate from the deepest horizons to the surface. When the water starts to migrate, the water can carry some clay, especially the clay. Why? Because clay is quite thin and light. So when water starts to migrate from the deepest horizons to the surface, the water brings and carry some clay to the surface. And then when the water achieves the surface, you can see this enrichment of clay. When the water achieves the surface, the water now starts to do a horizontal migration, like we can see inside the earth with the magma arcs that we can see the migration from the top, and then some migration that could be on the right, on the left. So we see this in an opposite direction, going in a horizontal way, that the water and the clay now starts to migrate to the left and right. Because of this, we have this expansion of the clay at the surface, and then you start to pull the coarse fragments to the material. You push then to the borders, and because of this movement, you have an increase of clay content inside these polygons, and your selection of gravels in the borders of these polygons. I will talk about more about that when we talk about the jelly soils. I will try to do some draws trying to explain much better this. Okay, don't worry for now. You just need to know that this kind of features only can be seen in areas with permafrost. And of course, we cannot see them in the tropics. You only can see them in Russia, Alaska, Antarctica, Arctic, some very, very close areas to polar regions or semi-polar or periglacial areas, okay? But definitely not close to equator. One of the suffixes that it's exclusive to the B horizon is the letter T. The letter T express clay migration, but not now. We are not talking about clay migration from the deepest horizons to the surface. Now from the surface to deepest horizon, okay? The letter T express that a B horizon that has a higher clay content than the above horizons, okay? So some clay migrate from the A or the E horizons and now concentrates at the B horizon. As you can see here, we have an A horizon here, we have an E horizon here with a light color, and we have this dark-ish color, very dark, a strong red color, and this very dark and red color express higher clay content, and this higher clay content came from these materials above. The clay from the A and especially from the E horizons, they migrate from here and now they concentrate in this specific horizon. So we say that this is a BT, a B horizon that has a higher clay content than the above horizons than the above sections of the soil, okay? We can feel this in the field. We just need to try and to measure the clay content in the field. And yes, it could be enough, but also we can see some clay films, some shine faces that tells you that yes, in this specific horizon or layer, we have some clay movement, some clay that came from another horizon and now it's deposited, it's concentrated in this specific horizon, okay? So this is a very good and easy example. You can see in this section below 30, 35 centimeters of depth, that this fabric, you can see the texture, the fabric of the picture is different from above, showing that in this section you have a higher clay content. And I'm telling you that this clay content came from the above horizons, the A horizon, okay? You also can see, as I said, the shiny faces. You can realize that here, if you put the sample against the sunlight, you can see that the soil start to shine. These shine faces, they are just an expression of clay movement, because the clay migrate from the A or the E horizons and concentrated in the B horizon. And when the clay concentrate in the B horizon, the clay concentrate at some millions of glasses that now are covering the aggregate, the pad. So you can see a lot of mirrors that are at the surface of this aggregate and just reflecting the sunlight. Because of this reflection, you see that this pad is shining, okay? The pad is shining because I have a million of clay minerals covering the surface of this aggregate, okay? So I have a lot of millions and tons of millions of clays that are covering the aggregate and reflecting the light, okay? This is one of the expressions showing you that yes, you register clay migration in this specific horizon, and because of this, you need to call it as a BT, a B horizon that express clay migration, okay? At the microscope, it's quite easy to see that, because at the microscope, we can see the voids between the aggregates. They are fulfilled by clay. You can see here, here, and here. A typical void should seem like this. You can see this white color, and this white color shows that, for example, between this aggregate and this aggregate, you don't have nothing. You have nothing. So basically water or air. But in this case, you can see even some layers. Can you see them? The layers? These layers are showing you that the clay is concentrated in the voids and deposit at the surface at the pads. So the surface of the pads are covered by clay, and in some cases, this covering, this fulfilling, this migration of clay is so intense that you decrease the conductivity of the soil. So the voids now, they are partially or completely fulfilled by clay. And because of this, the water conductivity, the water penetration through the soil, it's quite hard. So it's why we pay so much attention for these BT horizons, because now I need to consider that the water conductivity between the A and B horizons, they are different. The A horizon has, let's say, typical voids, and because of this, the water can easily penetrate through the A horizon. But when this water finds the B horizon, the BT horizon, the voids are partially or completely fulfilled by clay. So the water migration, the water penetration is not the same of the A horizon. The water penetration will be much more slow, And this slowly movement can induce some redox conditions, can induce some flooding of the horizon, can induce some erosion, some runoff, so can induce some problems. And even if it's not inducing erosion and runoff, I need to consider that it's not all the plants and all the land uses that are adjusted to this specific soil, because no one wants to live in an area that has some seasonal flooding, or no one wants to try to cultivate plants that cannot grow in flooded conditions in soils that are seasonal flooded. So we need to consider this, and it's why we need to pay so much attention to that. Okay, at the microscope, when we add the reflected light, it's amazing because we can see that this black line, these extension lines, as we call them in the microscope studies, they express a very good organization of the clay, showing that yes, these clays, they migrate from the surface and they were deposited at the surface of the aggregates in very calm conditions, showing you that this soil was formed in wet conditions, and this wet climate conditions, they were quite stable for a long time. Okay, we don't have a variation of between wet and dry or wetter and drier conditions. No, this extension lines is showing you that yes, this specific soil that you are studying, it was formed by wet conditions that keep for a long time. We don't know how much time we need to date these materials to know that, but at least we know that a long time is needed to form this. And they are showing that, yes, it was formed in wet conditions. It's why I'm saying that we can use some of this classification properties to understand much better about soil genesis. Of course, we are always trying to classify soil, trying to think about land use and genesis and or genesis. But we need to worry because some faces that also shine, they are not necessarily clay that migrate from the surface to the bottom or surface to deeper horizons, okay? We have some faces in horizons and layers that express the friction between one aggregate and the another, okay? Especially when we have horizons that are clay rich, and these clays are 2-to-1 minerals like illite, smectite, montmorillonite, some clays that can shrink and swell, can expand and contract. Because of this change of volume during the wet and the dry season, some of these aggregates, some of these pads, they can frictionate against others. And this friction can produce some shine faces. These shine faces, we call them slickensides. So these slickensides, they are not related to clay migration. They are related to friction between aggregates. Oh, JJ, how can I know that this specific soil is formed by clay migration or by friction? Yes, you need to check the texture of the material. You need to check the texture of the above horizons and that horizon with shiny faces. Of course, not only this, but also microscope analysis and some lab analysis can help you to identify and distinguish between them. But basically, at the first moment, measure the texture, the clay content of all horizons can help you to see the differences, because these slickensides, they are only formed in clay-rich materials, so they cannot register a variation of clay content between the horizons, okay? And they only can be seen in clay-rich materials. So I need to register a high clay content, and of course, this clay content should be related to clays with a high activity clays like 221 minerals, not kaolinite, not goethite, not hematite, not halezite. I need smectite, elite, high activity clays. Okay. Of course, you also can see that these high activity clays, they create like large cracks, as you can see here. Very large cracks, huge cracks. You can stop a car inside these cracks because they are really, really high. I'm just joking, but you can see how large they are. And these big cracks, they are related to a high clay content and also some uh, place that has high activity. So I can register if I find some faces that are shining. So yes, these faces, they are silicon sides, and I will use the double S letter. Okay, the double S suffix, I'm sorry. Uh, this kind of relief, it's quite common. We call it geogai. The geogai, it's a kind of micro relief. This geogai express the clay migration again because of shrinking and swelling, but now the clay migration again as the cryoturbation from the bottom to the top. This clay migration from the bottom to the top induced the formation of these hills, these mounds, okay? They are not related to biological activity. They are related only to physical properties of difference of temperature and difference of moisture between the deepest horizons and the surface, okay? So again, as in the case of the cryoturbation, the clay migrates from the deepest horizons that has a higher amount of water, a higher moisture. So the water migrates to the deepest, from the deepest to the surface horizons, and at the surface you have a higher concentration of clay that induce these hills, and these hills are formed by this clay migration. Okay, so you can see then in some cases they are not omnipresent, they are not universal in areas with silicon sides, but yes, you can see them in some areas. The age suffix, it's a suffix strict related to the B horizons, and this suffix express accumulation of organic matter. We already talked about this specific material, this dark horizon, especially this one. This and this one are horizons that should receive a BH legend, but in especially in this case, you can see a very easily dark color. This organic matter at this deep horizon, at this depth, is expressing clay migration. So the clay, the organic material migrate from the surface and it's concentrated here. And because of this, I will call it as a B horizon. And because of the concentration of organic matter, I should call it as a B age horizon. Okay, this age horizon expresses this dark color and the concentration of organic matter. So I can see that the sand and the silt particles, they are covered by clay, but now the clay, it's organic clay, it's organic matter. Okay, so I can see some organic matter coatings around the gravels and especially the coarse sand and the silt particles. Okay, this kind of horizon, it's more common in sandy materials, because at the sandy materials, the migration of organic matter can be done very easily. Okay, because when you register especially high precipitation associated to sandy textures, the water that penetrates through the sandy soil can bring some material, some organic material from from the surface horizons to the deepest horizons. And this concentration of organic material creates the BH. This BH horizon, it's quite interesting because express that in the past I register here at this specific level, the water table level. Okay, so this is quite interesting, especially for people that are interested in the studies of landscape genesis, the landscape evolution, because if I date this material, the organic material here, I can date the level of the water table. So I can note that, okay, the water table was at a depth of 50, between 50 and 80 centimeters depth in the last 4,000 of years before the present. So yes, it's a very good and interesting information, especially for people that wants to study interactions between soil and geomorphology. Okay. We also can use the letter S, and in this case, the letter S also express accumulation of material in the B horizon, but in this case, express accumulation of iron oxides, as you can see here. So iron and aluminum oxides, when they concentrate and they are accumulated in the horizons, like here, you also can see here, these colors express that organic matter migrate and concentrate in some region, but all iron and aluminum oxides, they also migrate and they concentrated here. So I call this as a S layer. So it's a BS. In this case, I have a BH and a BS, okay? Oh, yes, we also have carbonates. So the carbonates are quite easy. Here you can see some concretions or nodules of carbonates, okay? And they have this white color as the salt. So the difference between them is when I drop some acid, I can see some bubbles showing some reaction between the acid and this material, showing that yes, this material has some carbonates, okay? And I can register the pedogenic carbonate accumulation or concentration by the letter K or double K according to the volume, according to the amount of material. So if I have less than 50% of calcium carbonate, pedogenic calcium carbonate, so I use the K. If I have more than equal or more than 50% of calcium carbonate accumulation, so I will use the double K. Okay. Here I can see some examples. In this dark soil, these white spots, they are all calcium carbonate. So yes, I can just measure by volume how much of calcium carbonate I have, and I can use the K or double K. We also can register some cementation, not only by calcium carbonate, but by iron. In this case, I can use the letter M. JJ, we already saw that we can see some concretions and nodules of iron, and we use the letter C. Why now we are talking about the cementation again? Yes, because as you can see here, the letter M express a huge cementation of the material and creates a continuous or almost continuous layer, okay? So 90% or more of that specific layer or horizon should be cemented, okay? So this creates a huge problem to root penetration, to water penetration, to a lot of things. So in this case, I can see a layer that almost of the layer is cemented by iron. In this case, I use the letter M. The letter M should be combined to the source of the cementation, okay? So I can register some layer that's completely or almost completely cemented by calcium carbonate. So I use the letter KM or double KM. If I see this layer cemented by silica, for example, I can use the letter KM. If I see some salt, ZM. If I see some iron, SM. So I need to combine the letter M with something, Okay, so I need to combine the letter M with the source of the cementation, because I'm just saying that I have a strong cementation, and almost or 100% of that specific layer or horizon, it's cemented by something. So the most cases, the majority of cases, we have iron cementation, but we also can see others. So the letter M, I need to combine it with anything other that shows the source of this cementation, okay? The letter G is quite easy. It's quite easy because the letter G is related to the gray colors. So just think about gray, the first letter, G, it's related to iron reduction. So I register fluided conditions. Because of these fluided conditions, the iron oxides like goethite or hematite, they are destroyed, and now the soil color, the matrix of the color acts like a gray color without any hue. The absence of hue showing you that you don't have iron oxides, or at least they are not dominant, and then you use the letter J. The letter G, it's more expressed in fluided, in constant fluided areas, but of course you also can see in some areas that the fluiding is just partially or just in some specific months. Okay, but yes, shows you that that specific soil profile it's suffering in the past or today by reduction of iron. Okay. It's quite common to see in some cases some iron concretions here and iron nodules, some models that we call. These models, they expressing that the reducing conditions, they are dominant, but in some periods of time, in some months, I have some oxic conditions that can induce some iron oxidation and formation of models, okay? Oh, we also can see at the surface especially, but also in the deeper horizons, some physical root restrictions because of high bulk density, okay? So high density of materials induced or not by humans, they can show, for example, by roots growing in a horizontal way, showing that we have some problems to penetration, and we need to use the letter D for them, okay? Here you can see very easily how the roots are not growing very well in deeper horizons, but they are just growing in the horizontal way. And this is quite bad, especially for trees, because they cannot support very easily wind erosion and wind strength. In some areas, because of this, you can also register some flooding because of the root restriction. Also, it's related to low water penetration, low water conductivity through the soil, and you start to have some floodings. It's quite important to identify this in the field because it takes a lot of attention to land use. In some cases, we also can register the presence of sulfides like pyrite. Pyrite has this cubic, wonderful shape, and this wonderful mineral, it's composed by iron and sulfur. And because of the iron and sulfur in this case, they are reduced at iron and reduced at sulfur, they can be easily oxidized, okay? And the oxidation of these sulfides, they produce a high amount of acid and then produce soils with a very low acid. If you find sulfides in the soil, means that you need to pay attention to the oxic conditions if the soil is fluided, or you need to reduce or minimize the amount of oxygen that could enter the soil. So, for example, I should avoid to remove the water inside the soil, to drain the soil, because if you drain the soil, you can start the oxidation of sulfides and drop the pH to very low conditions. For example, the pH sometimes could drop to 2.8, 1.5, 0.5. This very, very low pH, they are quite bad for everything, for any kind of land use, for any kind of agriculture. Only some specific organisms can live in this acidic, extremely acidic conditions. So fine soils with sulfites, it's quite important to avoid to drain them if you can avoid to drain them. They usually register this dark and reddish color, and also a sulfur odor, like a smell of rotting eggs. Okay, you can feel them in the field. It's quite easy to feel them in the field. You feel like something is not good, like rotten eggs or rotting food, something it's really, really messed. And you also can find some soils that are red or oxidized, that the sulfides were red oxidized. And in this case, you use the letter J to express the presence of jarosite. So you can see in this specific soil that it's fluted, because you can see the water table here, and you also can see this yellowish colors. These yellowish colors, they are not related to goethite, but they are related to jarosite. In this case, the jarosite, it's a sulfate formed by the oxidation of pyrite, and shows that, yes, this soil registers very low pH. The problem, it's a red here. So now we need to consider how to use or try to preserve this very acidic, extremely acidic soil. Here you can see some photos showing the presence of the jarosite. Okay, this yellowish color, it's related to the jarosite. And of course, at the field, I can feel very easily that very strong odor, the very strong smell of rotting eggs. Okay. Yes, again, the cementation of soils can be done by carbonates. Here, just to show you, I think that I missed something. This photo should be in the other area. Just the cementation by calcium carbonate, you can see here, okay? You even can see some marks of the roots trying to grow through this horizon. If you use your knife or even a hammer, it's quite hard to break this layer because everything is cemented by calcium carbonate. So in this case, I use the key M or the double key M according to amount of calcium carbonate. In this case, double key M. In this case, cementation by iron, and now cementation by silica in some specific horizons, especially in very dry conditions. You can register some accumulation of secondary silica, and then the silica can cement the soil and produce what we call some cemented horizons as fragipan, or soils or horizons or layers with fragic characteristics. What are these materials and how they are formed? Okay, in some conditions, especially as I said, in very dry conditions, you can register some salt concentration at the surface, right? Because the water migrates from deeper horizons to the surface, and when the water achieves the surface, the water evaporates, and this water brings a lot of calcium, sodium, chloride, bromide, and other anions and cations. And when the water just evaporates, these elements, they combine and crystallize as salts. Okay, when the wet season comes, the rain starts to achieve the surface of the soil, start to dissolve the salts, and the salts, they increase the pH of the soil, but only at the surface. So the pH of the surface could achieve 9.8, 10 dot something, like 10.5 or even 11.2. So this very high, very high pH starts to dissolve the silica, because silica is very easily to dissolve at a very high pH, especially at pH above 8.6. So above this pH, very high pH, the silica, it starts to dissolve, and the water can migrate through the soil profile, and the water can carry some of the silica from the surface to the deepest horizons. At the deepest horizons, we don't register a lot of salt concentration, so the pH is not high. Because of the dropping of pH according to the depth, this silica starts to concentrate, starts to reprecipitate. And when this silica precipitates, it acts like a gel and starts to cement the horizon, cements the layer, okay? So I can register only accumulation of silica, or I can register even a kind of cementation. If the cementation is weak, if I can easily broke it then with my knife, or even if I put a piece of this layer in contact with some water, and after some minutes, this piece starts to dissolve, this material starts to break to powder. So great, I have the fragipan. I have a layer or a horizon that register very strong cementation, but this cementation can be dissolved with water, or I can break them even with my hands, okay? So the cementation is hard, but it's not too hard to be broken, indicating that yes, I registered some silica migration and silica cementation, okay? When I check these horizons at the microscope, I can see something like this. You can see that only some voids are showing like this. This is a void, this is a void, this is a void. But the majority of the soil you can see here is fulfilled by something with this white or yellowish color, showing that the majority of horizon or layer is basically fulfilled by silica. So the material is very well cemented. I don't have a lot of voids in this horizon or layer. Another suffix that's quite important and interesting is the N suffix, that express a high percentage of exchangeable sodium, okay? Of course, we don't have anything that could tells you very easily that yes, you register a high sodium accumulation in this specific horizon, but you have some tips, okay? One of the tips that you can use, of course, is this kind of columnar structure. This columnar structure shows you that, yes, in this specific case, you can register a high sodium content, okay? Why this columnar structure tells you that you register a high sodium percentage in this case? Because this columnar structure is formed by clay migration from the deepest from the top to the deepest horizons, especially the B horizon, okay? But this clay migration was induced by salt, and especially by sodium. So let's talk about this, okay? When you have some concentration of salt at the surface, as I mentioned, this is quite common in dry conditions, in very dry conditions. When the wet conditions arrive, oh, sorry guys, just give me 1 minute because I need to plug my computer in the sock. Just a second. Or my computer will turn off. Great. So let's go back. So as I said, some of dry areas can concentrate salt at the surface, and when the wet season arrives, the rain starts to dissolve some of the salt, and because of this salt, especially sodium concentration very high at the surface, the sodium starts to break some of these aggregates, starts to disperse clay. And the clay now, the free clay can migrate from the top to the deepest horizons. And this clay starts to concentrate in the deepest horizons, in the B horizon, but especially at the top of some prismatic structures. So this concentration of clay creates this kind of concave shape at the top. Why? Because between one aggregate and another one, we have a void. We have a void, a pore that can concentrate clay inside itself. And this creates like a void that can suck some kind of material, some kind of clay to inside the void, and then create like this concave shape. So you don't have a lateral concentration of clay that comes with the same shape from the deepest to the topest positions of the aggregate. You create some kind of a concave that's a more equilibrated shape in the nature. So you create some pads with a concave shape on the top related to this clay migration from the top to the deepest horizons. I will talk more about this when we talk about planosols and solonets and some alphasols, especially in the driest regions. But for now, you just need to memorize that, okay, this kind of feature express that maybe I register a high sodium concentration. Okay, it's one of the tips that shows you that you have a high sodium concentration in your soil. This suffix, it's one of the most common and most easiest. It's the O suffix. It's only used to B horizons, and in this case, it expresses residual accumulation of Sesqui oxides, or basically iron and aluminum and titanium and manganese oxides. So when you have a deep weathering, a deep leaching, you start to destroy the 2-to-1 minerals, and in sometimes even to 1-to-1 minerals. So because of this intense destruction of this 2-to-1 and 1-to-1 minerals, you induce intense clay removal, especially the silica removal, and you only concentrate the iron oxides and aluminum oxides because they are quite stable, because they cannot be destroyed by this low pH. And then you increase the relative concentration of aluminum, iron, manganese, titanium in the soils, and you start create a soil with a high capacity of absorbed anions, not only the cations, because of the positive charge at the surface of the iron oxides, the aluminum oxides, the manganese oxides, the titanium oxides, and then you start to accumulate something that's produced by a deep weathering. We can easily find this kind of horizons in the tropics. They present some fertility problems, fertility issues that we can solve them very easily when we plan very well. But something that's quite good is that these soils, they have very good physical behaviors. They can storage a high amount of water for the dry seasons, and they shows you that in that specific area you register in the past stable conditions and climatic conditions. So tectonic stability and climatic stability, they are needed to form, to create a BO horizon, because you need a very intense leaching and weathering to create something that concentrates the products of weathering, especially iron and aluminum oxides. So you can see then reddish, yellowish, depending on the amount of iron, the parent material, the amount of organic matter, the type of mineral that you can register. It's goethite or hematite. We also can use the W suffix. The W suffix, it's used to incipient wafering. Okay, so the word means wafering, showing that you register now a B horizon that at least it's formed by an incipient wafering. So a little of wafering, a little of leaching starts to create a B horizon, but I cannot see any other process, any other more complex process than wafering and leaching. It's forming that specific P horizon. So it's just to show you that you have one specific section of the soil that's not rich in gravels, is not rich in rocks. So it's not a C horizon, it's not a dark horizon like the A, it's not a light horizon like the E, but I can see some structure, some pads, some aggregates. So it's a B horizon, but a B horizon without any specific process or more complex process than only watering and leaching. Okay, this BW horizon, it's quite important because we have some orders and some soils that only register the B horizon, and because of this we will classify them according to this BW horizons. Okay. Oh, we also use the letter R. The letter R is used only to the sea horizon, okay, or the sea layer. Of course, when you can see some materials that show the bedrock, so you have a wet red or soft bedrock that you can broke easily with your knife or with using your shovels or your hands, that you can see the parent material, but the parent material was already destroyed or wet, okay? So for example, here I can easily broke some parts of this material showing that yes, this is a CR. I can easily broke some of these parts with the shovel of my hands or knife. So yes, no problem. Here, both cases, okay? I can see some structure related to the parent material, especially because of this pink color, but I see that this material was wafted. So it's not a fresh rock. It's something like a soft rock. So I will use this CR. We also can use this CO, especially for the L layer, when we have some materials like organic materials that was deposited underwater. So you should remember the laminic materials, those organic materials that were decomposed in lakes, in marbles, in some fluid areas. So this expression of biological activity can concentrate some organic material. And we also can register some mineral materials in these fluid conditions too. As you can see here, I can see some mineral materials, especially some silica materials deposit in lake conditions, in fluid conditions, okay? I already show you also this picture showing that we have some mineral concentrations related to this very calm conditions in lakes. Okay, guys, now we saw all the suffixes that are related to soil taxonomy, but we have a lot of time. So my suggestion is that we can stop for 15 minutes and then we can return at 10 and 45, okay, according to the Brazilian time, and then we start to talk about soil classification, okay?
Okay, sir. Okay, sir.
So hello everyone, let's go back. Sorry, here. So now that everyone knows the basic definitions of soils, now that everyone knows the master horizons and layers, and we saw about the suffixes, we can start to talk about soil classification. Great, 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 great. And the first step is to understand how you classify soil. The first step to classify a soil is, of course, to dig a soil profile and to stand, to check the soil morphology, to describe the soil morphology, to identify the horizons, and then we can have some notes about the descriptions, the properties, and the characteristics of each of these layers and horizons. Okay, something that's quite important to highlight here is that when you are in the field and we are describing the A, B, E, C horizons, layers, we are talking about genetic horizons and layers. We are talking about horizons that are formed by pedogenesis, okay, and then we call them as A or B or C or E according to their properties and morphology. But to classify soils, we need what we call diagnostic horizons. What are the diagnostic horizons? I'd like to call the diagnostic horizons as special genetic horizons. So the diagnostic horizons are those genetic horizons that fits specific criterias. They fit specific properties, specific characteristics. Let's think, for example, the presence of concretions and nodules. We saw that we add the suffix C. So if I find a horizon with concretions and nodules, I can call that horizon as a BC. Okay, but if I find a specific horizon with one specific amount of concretions and nodules, or a specific size of these concretions and nodules, then I can fit this genetic horizon into a diagnostic horizon. Okay, because this genetic horizon fits some specific criteria. For example, the amount of concretions and nodules, the size and the connection between these concretions and nodules. So the diagnostic horizons, all of them, they have specific criteria, and the majority of them, they have quantitative criteria, like which color that specific horizon should fit, which amount of concretions, nodules, clay skins, vertic, and vertic properties like these lichen sites. Each property, each characteristic should be measurable. I should quantify it, and if this quantity, if this amount fits the criteria, then I can identify the diagnostic horizon. Okay, let's show another example just to make 100% clear. We saw about the BO horizon, that horizon that's formed by deeply wafting and leaching. Okay, so if I see horizon with deep wafting properties, like I can see that it registers low activity clays, probably a high amount of goethite, hematite, gibbsite. So it registers a concentration of aluminum and iron, manganese, or titanium oxides. Great. I can call it as BO horizon. It's a genetic horizon. But I can find some specific diagnostic horizons that they should fit, for example, very, very low CEC per clay, showing that the wafering and the leaching, they produced a very low CEC according to the amount of clay. So if that BO horizon fits this minimum CEC, or in this case, the maximum CEC, yes, I can call it as one of the diagnostic horizons. So we will see that the diagnostic horizons, they differ from the genetic horizons because all of them, they have specific criteria, they have rules that should be followed to identify one diagnostic horizon. So when you go to field, we start the description of each genetic and its genetic horizon or layer. And after that, we start to identify the diagnostic horizons. Okay, so this B horizon is this specific diagnostic horizon. Okay, this C horizon is this specific diagnostic horizon. Oh, this A horizon, it's this specific diagnostic horizon. Okay, so some of these horizons, they can fit directly to diagnostic horizons, and some of them cannot. Okay, so we can register, of course, all soil profiles with genetic horizons and layers, but some of these soils, they cannot register a diagnostic horizon. None of them. They can register zero diagnostic horizons inside all the soil profile. And we have some cases with this, and this is not uncommon. This is not rare, especially in some areas in dry lands and also in steepy lands when the slope is quite steep. So in some cases, we don't have diagnostic horizons, okay, maybe just one of them, but it's not uncommon to find soils that they don't register diagnostic horizons in these cases, okay? And also we use other kind of proxies to identify and classify the soil, not only the diagnostic horizons, but also the diagnostic characteristics, because some characteristics, they are not related straight related to a horizon, but more like a characteristic, and they can occur everywhere. So they are produced by pedogenesis, but they are not related to one specific horizon. So we call them diagnostic characteristics. So after the description of the morphology, after the identification of the genetic horizons and the layers, we will identify the diagnostic horizons. We must identify the diagnostic characteristics, and then we can classify the soil. Okay, so only after the identification of the diagnostic horizons and characteristics, so we can classify the soil. Okay, what we plan to do now, we will start to talk about the diagnostic horizons, especially what we call app patterns, the topsoil, the surface horizons, okay? Just before talking about the topsoils, the app patterns, just show you what we see in soil taxonomy. In soil taxonomy, we classify the soils in a hierarchical way. So we go from the most general classification, that's called order, and we go to the deepest and more complex and more systematic, that's called series. So we go from orders to series, and we start with 12 orders, and we can achieve more than 1,000 subgroups and a huge amount of families and series. Okay, to classify a soil in the order level, in the first level, we use the diagnostic horizons. To classify the soils at the suborder level, we need to use the diagnostic characteristics and sometimes also diagnostic horizons. At the grade group, also diagnostic characteristics, diagnostic horizons. At the subgroup level, we need to identify if that specific soil has typical or unusual characteristics. At the family level, we need to consider aspects that are important to management, to the land use, and to the last level, at series level, we could consider the morphology. We should consider the morphology, okay? In this specific case, as we don't have a lot of time, we will focus more on the order level because it's the most important. After that, we can see some suborders, but I will try to focus more on the most important suborders, okay? And of course, trying to show you how to classify in the lowest levels after the order and suborder. Because once you understand how to use this soil taxonomy book, you can easily understand and classify everything, okay? Oh, sorry. So let's start with the app pattern. And the app pattern, it's the diagnostic horizon that's formed at the surface or close to the surface. So we call as app pattern only those diagnostic horizons that are formed by surface process or surface that act close to the surface, okay? And of course, it's quite important to consider that these app patterns, they don't register rock structure except by one. I will show you today this exception, but all of them, they don't register a huge amount or a huge importance or a huge influence of rock structure because the surface processes are more related to the addition of organic matter, to the addition and stabilization of organic matter, to human actions. So these process and these properties are much more important than the amount of rock structure, okay? These app patterns, we need to differentiate them according to the color. Some of them express alluviation, so the color is in general quite dark. Some of them present some reduced clay content because they lose clay, okay? Some of them could register human action, okay? Some of them can register surface mantle of new soil material or human transported materials that was eroded from upper areas or materials that was transported by humans, okay? All of them are related to app patterns. And here we have all app patterns that we have according to soil taxonomy: the anthropic, holistic, histic, melanic, molic, ochric, Pelagian, and umbric. Okay, let's start with the anthropic app pattern. And the anthropic app pattern, it's quite easy to identify it because it's a mineral soil material. So the organic carbon content, it's below 12%, and it has some strong influence of humans. So I need to identify any kind of human action that deeply affected the properties of that specific horizon. So I can register any kind of materials that was altered, added, transported, removed by humans, okay? They could be related to urban areas. They could register alluviation. They in general present very high phosphorus and carbon content because especially the ancient humans, they add a lot of organic material at the top of the soil trying to improve the soil fertility or not. They can do this intentionally or not, but they add more carbon, they add more phosphorus, and of course the human action also add a lot of artifacts. So I already show you this photo. In this photo you can see this very dark horizon, and it's very, very thick more than 100 centimeters, 150 centimeters, but it's everything at topsoil because everything was produced at surface by human action. Why I'm saying that? Because this white fragments, they are just shells and bones added by humans, and this are related to human action trying to produce one of these soils with a higher positions that could be have a strategic position, and then um, they could survive to human invasions, to other tribes that try to invade in that specific area. The people from archaeology, they work a lot with this kind of a pattern, especially people that works with soil, but also with archaeology. They also pay attention to this kind of horizons. These photos, they were took in a microscope, and they show you, for example, some charcoal fragments. So these charcoal fragments are showing that humans, they burned something in that specific soil, producing charcoal, and this charcoal producing, it's one of this one of these criteria that can be used. It's quite common to find some artifacts, like some old shards, some kind of ceramic, and these fragments are ceramic, sides of ceramic that are inside the soil. This is a bone. You can see a lot of calcium, especially calcium in this area. And this bone, it's showing that this material was added to soil. These two soils, they are very, very easily to describe. They have some of artifacts like bricks. So you can see in both cases, bricks showing, and also some concrete layers showing that, yes, you have a deep and intense human action. And as I said, the criteria to identify an anthropic horizon. As I said, we have some criteria. Now we are talking about diagnostic horizons. And all diagnostic horizons, they need criteria. That specific soil that you stand, you describe, and you sample it, they need to follow some criteria. Okay, if they follow that criteria, all of them, or at least those criteria that are they are mandatory. So yes, you can call that as a diagnostic horizon. If they don't follow all the criteria, or at least the mandatory criteria, no, you cannot call it as the specific diagnostic horizon. So which criteria are mandatory to the diagnostic horizon called anthropic epipetal? First of all, when dry, this soil has structural units with a diameter of 30 centimeters or less. So I need to register pads, I need to register aggregates, and these pads or these aggregates, they should have 30 centimeters or less when dry. This is quite easy to identify in the field, so just check if you can see any kind of structure. Great, it has the structure, and the pads or the aggregates, they has less than 30 centimeters or equal to 30 centimeters. Next step. It has rock structure, including fine stratifications that it's 5 millimeters or even less than that, but this rock structure is less than 1/2 of the volume of all parts. So if I have more than one A horizon, so A1, A2, A3, so all of these parts, I need to register that I have less than 1/2 of the volume with rock structure, okay, in each of them. So A1, I need to register less than 1/2, A2, less than 1/2, A3, less than 1/2 of rock structure. If I have more than 1/2, no, I need to exclude. I'm not talking about an anthropic horizon, okay? An anthropic epipetal, an anthropic diagnostic horizon, okay? Also, the anthropic epipetal should register an N value that has less than 0.5 or a fluid class of non-fluid. And what the hell is that, right? This N value is one kind of lab analysis that people runs to measure the ability of soil to support loads. Okay, and we also have some influence of water, how the texture and the soil organic matter. So this N value, it modified by the water, the texture and the soil organic matter. But of course, we consider that at lab conditions, we can measure everything and be sure about the N value. We usually don't measure this, at least in Brazil. I never saw people spending time of this because they pay more attention to this, the fluid class of a non-fluid. So this specific layer or horizon, it has a behavior like a solid material. So it doesn't has as a fluid class, a fluid behavior. So it occurs, it behaviors as a non-fluid material, as a solid. Great, it could be an anthropic pattern. But let's keep going. You can see that all of these criteria, they are all of these criteria, they are mandatory because it's and. So to identify an anthropic pattern, at least I need to follow this three. If one of these three are not followed, if the horizon that you are describing didn't fit one of these three criteria, you are not talking about a diagnostic horizon, call it anthropic pattern. Okay? So let's go to the others. Okay. Oh, sorry. Let's go. Okay. Okay. So it should be formed by human altered or human transported material. Yes, of course, we are talking about an anthropic pattern. Okay. And anthropic landform or microfeature. So that material which composed the soil should be something that was transported or modified by humans. And also in some cases, I can see some anthropogenic landform. It's quite common in South America. People, they create some layers of soil, and of course in Europe we also can see that some layers that are quite flat at the surface because humans, they bring material from different areas, and when you have a steepy slope, you create this kind of partner surfaces that has a very gentle relief, and then you can produce some food and you can do some kind of pasture or agriculture in these areas. These kind of landforms, they are produced by humans, and because of this, you also can use it to identify the anthropic pattern. Okay. Of course, besides that, you need to find something that directly overlay mines or dragged sport material that has this rock structure. So you can see that any kind of material that was mined and modified and transported by humans, you also can find the anthropic pattern if this specific layer directly overlines this material that was mined, okay, and transported and verified by human actions, okay? Oh. And of course, another option, because now it's or, one of the options is that I register one or more of the following statements. That specific horizon or layer register artifacts, materials induced and then transported or added by humans. That okay, and these artifacts, they should be other than agriculture amends like Chimeline. So it's not just adding fertilizers, should be something big, something that really changed the structure and the fabric of the material, okay? And of course, not later discarded by humans. Or the other option is to register meeting material, okay? For example, eating and cooking waste and associated charred products, something that express that that area will support that humans in some time, okay? And another option is untracked conditions. The untracked conditions, they are observed, they are found in soils that were flooded by humans. For example, rice fields. It's quite common in rice fields that the humans, they flood that area, they induce the flooding. And that flooding, it's called untracked conditions. We have aquatic conditions, we have flooded conditions, but these flooded conditions, they were induced by humans. So we call it untracked conditions, okay? So if I found at least one of this or this mined material, so I can also keep calling that as an entropic pattern. But I have more criteria, okay? I need to find a minimum thickness, that it's the entire thickness of the soil above our root limiting layer if one occurs in the first 25 centimeters below the soil surface. So I need to find that, okay, I find a root limiting layer that's at 10 centimeters or 5 centimeters or 20 centimeters or 25 centimeters. I have something that avoids root growing in the first 25 centimeters. And the entire thickness of this material between the surface and the root limiting layer, it's basically just one horizon. So yes, I can call it as an anthropic pattern. Or if I don't have this root limiting layer, or if this root limiting layer is very, very deep or deeper than 25 centimeters, and I have much more than just one horizon, but this surface horizon, this topsoil has at least 25 centimeters. So I forgot to mention, it's not 25, it's at least 25 centimeters. Yes, you can call it as an anthropic pattern. Okay, so you see that we have specific criteria, we have specific rules that should be followed. Okay, so for example, if I don't follow the minimum thickness, so it's not an anthropic pattern, even if the anthropic pattern fits all of these criteria. So follow 1, 2, and 3, follow 4A, 4B with the artifacts, but the minimum thickness, the thickness of that specific layer or horizon is just 10 centimeters or 5 centimeters. Or I don't fit this criteria that the whole soil is just one horizon with the same properties that I mentioned until I found a root limiting layer. Okay, so all the mandatory criteria, they should be fulfilled, all of them. If one of them it's not fulfilled, it's not fitted, I cannot call that specific horizon as a diagnostic horizon. In this case, I cannot call it as an anthropic pattern. I need to fit, I need to follow all the criteria, okay? There's no criteria that's more important than the other. All of them has the equal weight. All of them are important at the same way, and I need to follow all of them. Some people doesn't like this very much, because sometimes you can find a soil or a horizon or a layer that has basically all the properties, all the characteristics, all the morphology of something, and they want to classify as a diagnostic horizon, but they can't, because, for example, the thickness, it's not the minimum thickness that it should be. So create something like, okay, I want to classify it, but I can't because the thickness, it's not fitted. And people start to argue about this, but we need to follow these rules because they were created considering that, okay, Even the minimum thickness express a minimum thickness that could affect the land use. If I register a human action, but this human action is quite thin, like covers just the first 5 centimeters. So maybe this is not a big deal. Maybe this is not affecting the land use. Maybe this cannot affect deeply how humans use and should consider that soil. Even the plants, even the animals, no one is paying a lot of attention on this very thin layer. So maybe we don't need to classify. And even then, we don't need to ignore the suffixes. Even, for example, a suffix AU or AP, this consider that, yes, we have some artifacts, for example, but because of the thickness, I cannot call it as an anthropic pattern. But in the genetic way, I can keep calling it as an AP or AU horizons, but I cannot identify the anthropic pattern. I cannot identify the diagnostic horizon because that specific horizon does not fit all the criteria. I think that someone raised a hand. Let me just check. Yes, please.
Yes, I was going to ask this criteria. Is there no is there no room for plus and minus, because it seems to me that it's rigid, that if you can't get one, then it's not. So is there no possibility that you can have some little a slight, one of the criteria is not really fitting in properly, but almost near? I don't understand. So I don't know whether it's not possible, because I don't know whether this criteria can always be, whether you can always get everything about the criteria at all times perfectly. So
Okay.
I just wanted some clarification.
I see. Let's see, for example, this one. Okay, let's just return. Okay, for example, in this case, okay, let's see that in this case, we have a root limiting layer here, and we have a lot of bricks, a lot of material. This has a thickness of 80 centimeters. Okay, so at least the minimum thickness of 25 centimeters, it's fitted, and I can see bricks, and I can tell you that this material has a solid behavior. So all of these criteria, it's fitted. Let's say we cannot see very easily, but I can assure you that it has pads, it has structure units. We cannot see a lot of rock structure in that photo. And I'm telling you that the behavior is like a solid, it's like a non-fluid material, okay? And yes, we can see that this material has a lot of artifacts because you can see the bricks, okay? And okay, we don't see equic because here you can see the ore. So because I can see the artifacts, I don't need to fit this or this. They are not mandatory. If I fit this, it's okay. Okay. If I don't fit this one, I can fit using this. If I don't fit this or this, I can use this because I have the ore in this case. Okay. It's the same case for this one. For example, I cannot see in that photo material from mining, but I can see the artifacts and I can see the ore here. So this or this, if I fit this one or this one, I already have an anthropic pattern. JJ, what happens if I fit both? Great, no problem. But you need to fit at least one of them, okay? This one or this one, okay?
Okay, thank you very much.
Welcome. Good question. Because I think that after some diagnostic horizons, they will be very easily to see these differences and understand very well what is mandatory and what's, let's say, not mandatory, what is optional according to the or and here. Okay, so you just need to pay attention for this. And guys, again, You do not need to memorize everything, definitely, because it's quite impossible. Okay, no one memorize everything because it's quite hard. It's a lot of information. It's a lot. So when you go to field and you start to describe something, and okay, let's identify the diagnostic horizons right now. What you need to do? Open your soil taxonomy hard copy. You need to do that. So every time that you go to field, you bring your hard copy with you, and you need to read and check all these criteria, all these details. Okay, don't worry about like, oh, I'm seems like a student, or I'm seems like a non-experienced person. No way, guys. Everyone, even the people who wrote the soil taxonomy, they bring the hard copy with them because they really understand that they need this material to classify correctly the soil, because they really know that we have a lot of criteria, we have a lot of information. It's quite hard to memorize everything. Okay, so don't worry, don't be worried to bring all of this. I have hard copies here, that every time that I go to field, I bring them with me, because I understand that yes, I cannot memorize everything. My memory is not so good. So yes, I need to use the hard copy to be sure that I'm using all the criteria. Okay, so don't worry about that. Don't worry about bringing your hard copy to the field. And again, don't worry to memorize everything. What is really important, understand what is the conception, the definition of that specific diagnostic horizon. Okay, what is important? So artifacts, mining tails. When I go to a urban area and I can see artifacts, or if I go to an area and I can see some ancient evidence of humans, great. Both are good, very good concepts and criteria that I really need to check if they fit the minimum amount, and then I can classify as a diagnostic horizon. No problem. Another diagnostic horizon is the pholistic app pattern. This pholistic app pattern, it's great because it is composed by organic soil material. And we already know what is organic soil material. Organic soil material is that material with a minimum of 12% of organic carbon. Okay, and we already know that the minimum of 12% of organic carbon means that we have an O or age, or O horizon, sorry, the age is for just for WRB, I'm sorry. So we have an O horizon, and the O horizon is the genetic horizon. The pholistic app pattern is the diagnostic horizon. So if I register an O horizon with some characteristics, so maybe I can call it as a pholistic app pattern. So let's check. The first of all is that I need to register a high content of organic carbon, at least 12%, 2%. This specific soil or horizon or layer should register a low amount of days with saturation. So the saturation, the fluting should register less than 30 cumulative days. So I need to consider that this specific horizon is not formed by fluid conditions. So the organic accumulation, the organic addition, it's related to, for example, cold conditions, very cold conditions, very low temperatures, or because, for example, the aluminum content is quite high, or the calcium content is quite high, and this also favor the concentration of organic carbon, or the clay content, something helps and yields a higher concentration, a higher content of organic carbon. But definitely it's not water, it's not fluid conditions, okay? Also, we can see some fields, some areas that they are induced by humans. So humans also can add the organic carbon content quite high. And in this case, I should call it as a holistic pattern if it fits the holistic criteria that we will see, okay? And of course, this holistic pattern, it should register let's say dry conditions or non-fluided conditions. So it also cannot be artificially drained. So it should be naturally formed in drained or well-drained conditions. As I said, the fluided conditions did not format this specific soil profile, does not format this specific horizon or layer, okay, but other process that induced organic carbon accumulation. So we can see some photos like this, both photos, okay, areas that register some specific conditions that are not related to fluided areas, especially this one in very cold climate conditions, okay. This photo on the left, it was taken in areas that the temperature is around 8.4 Celsius degree. So this very low temperature limits or avoid the microbial activity, and because of this microbial activity, it's limited. The decomposition of organic carbon is limited, and because of this, you can concentrate some organic carbon, okay? So now let's see the criteria. First of all, the organic soil material should have at least 20 centimeters or more than this. And if this material contains 75% or more of fibers, sponginal fibers, okay? Or has a bulk density when moist of less than 0.1 grams per centimeter, 30 centimeters, okay? Or, okay, 30 centimeters or more thicker than this, or I have an AP horizon that when mixed to a depth of 25 centimeters, the content of organic carbon is at least 8%. So let's see the first two options. You can see that I have or and or here. So at least one of them I need to fit, okay? If I fit one of them, great, no problem. First of all, see if the horizon is basically composed by fibers. So I have a high amount of fibers, very low decomposed organic material. So the thickness should be 20 centimeters. Or if I register a very low bulk density, I register at least 20 centimeters. If the content of fibers is not so high, or if the bulk density is not so low, I need to register at least 15 centimeters. So you can see that here the thickness is larger than this because I'm considering that I have more in the non-decomposed or little decomposed materials. So in this case, because of this low decomposition, we increase the thickness, considering that, yes, we need to think about soil, not only about liter, okay? So if the material is more decomposed, I don't register a lot of fibers, or I don't register a very low bulk density. So, okay, just 15 centimeters, it's okay. Or the last option is that I register an AB horizon. What is an A horizon? A horizon formed by humans, or a horizon at the surface with dark colors. And we know that the letter P expresses some agriculture, like mixture of material, addition of fertilizers. So if I register an A horizon that's formed at the surface, and it registers intense human action, but it's not an anthropic pattern, and when considering the minimum thickness of 25 centimeters, the organic carbon content is 8% or more than this, then I can call it as a pholistic egg pattern. So you can see that pholistic egg patterns, they can be formed naturally or they can be formed by humans if the content of organic carbon is at least 8%. Okay, so in both cases, letter A and B, in the number one, the content should be 12%. Here, the content it's less than this, just 8 is enough. Okay, we need to follow this criteria to identify the pholistic egg pattern. And how you can easily identify it in the field, because in the field, I cannot see anything more than just the thickness. I hardly can see the amount of fibers, and I hardly can measure the density at the field or the organic carbon content. So what we can do, we can predict the low density, okay, using a piece of material. As I said, we can easily take large pieces of the soil of the horizon and feel that the density is quite low. As I said before, these organic layers in horizons, they vibrate and shake very easily because they has a very low bulk density. They also can present some cracks when they dry because the organic matter absorb a lot of water, and because of this, when the organic matter dries, it reduces the volume and shows some cracks, and of course the very dark color. So we have some tips to identify this kind of diagnostic horizon in the field, but only after the lab analysis that measure the organic carbon content. Yes, you can be sure that we are talking about a pholistic egg pattern. Okay. Let's see the last diagnostic horizon for today, the HISTIC egg pattern. The HISTIC egg pattern, it's also an organic soil material. So the organic carbon content should also be 12% or more than this. But in the opposite of the pholistic, the HISTIC egg pattern, it's saturated by water. So I need to register at least 30 cumulative days, 30 consecutive days that register a lot of water in that specific area. So that area is flooded, and the flooding is the main process that induces accumulation of organic carbon. Okay, it also could be cultivated soil mineral. Okay, when we have some humans adding some material, and of course some of these HISTIC patterns also they can be artificially drained by humans, but they keep as HISTIC patterns because they were artificially drained. Okay, so let's see the criteria. Basically quite similar to the other, but now the thickness is a little thicker. It's larger than this. It's higher than before. So consists of organic soil material with 12% of organic carbon at least. And I need to register 20 to 60 centimeters of thickness if I register a lot of fiber or a bulk density less than 0.1. So if the density is quite low, or if I register a high content of very low decomposed material. This, if it's not the case, if I don't have a lot of fiber or the density is not too low, I need to register between 20 to 40 centimeters of thickness. Or the other option is that I have a horizon that's formed by human action, and in the first 25 centimeters, the organic carbon content is at least 8%. So we can see basically the same criteria here, except by the thickness, that here it's higher. And of course, we need to consider that in this case, in the HISTIC horizon, we are talking about a diagnostic horizon formed by initially, at least by flooded conditions, okay? Or fluid formed in fluid conditions and then artificially drained by humans. Okay? So these three diagnostic horizons already tells you a lot about soils that are formed by humans, and this is the main characteristic. Soils with a high content of organic matter that are not formed by fluid, or soils formed by human action with a high content of organic carbon. And in the last case, horizons that I register a high content of organic carbon, but in this case, they were formed by flooding, or they were formed by human action, but still with a very high organic carbon content. These three diagnostic horizons are quite easy to distinguish between them because they are quite different. We have some other options in the next steps that could be more similar, and because of this, we need to pay more attention to them, okay? But for now, it's okay. For now, it's quite easy. Guys, I will stop here now because I know that's a lot of information. We saw all the suffixes and we already saw three diagnostic horizons. As I said, tomorrow I will share a record about the next soil diagnostics. I will record a class about some of these diagnostic horizons and I will share with you so you have all the week to watch this recording before our next class. Please do that. I will email you again to let you know that, guys, I already share all the slides, I already shared all the recording. Please be sure to watch it before our next class, just to be sure that everyone is updated with our class, okay? Guys, again, if you have any doubt about anything, just let me know. If you are too shy to ask something right now, don't be that. But if you prefer, you can email me. Don't worry about that, and I can help you with that. Okay? So see you on next Monday. And until that, I will share the recording of our next class. Okay? So guys, see you. Have a great week. Bye-bye.
Bye-bye, and you too.
Thank you. Thank you.
Bye, Prof.
Bye-bye.
Ciao.
Ciao.